Okay, welcome everybody. Just a first couple of really strict rules for the session. If you've got a question in your head, just ask it. Please don't wait, please don't be polite. Just say, Kevin, Tony, I have a question, I need it answered and I need it answered now. The problem with waiting to ask questions, sometimes you forget and you leave the session and you think, oh, I wish I'd asked that question. So that's the only real rule. If you've got a question, interrupt us. Please do not be polite about waiting to the end. It's important that we answer your questions. Before we start with the slides, I just really want to introduce you to this gentleman. A gentleman called William Edwards Deming. I don't know if anybody's familiar with this gentleman. After the Second World War, he was an American engineer, statistician, and author, but he went into Japan and he looked at the Japanese industry. And he is the father of the processes that revolutionized the way that Japan and Japanese industry worked. And he had a very important saying, and this is worth remembering. It's a little bit harsh, but it's true. If you cannot describe what you are doing as a process, you don't know what you're doing. And if we had a much longer session, if we had a lot more drillers in the room, the first task we usually do in a workshop like this is to get them to define the steps of making a connection on the rig. And it is amazing. You can have a room full of people working on the same rig together for a long period of time, working for the same company, and you ask 4 groups of those people to tell you how they make a connection. Not once in all the times I've done that have I had the same answer and the same process on each board. And it's absolutely critical if you're going to optimize your drilling at all, that you first understand what it is as a process. You need to break down each operation into a sequence that you understand. And you also need to understand which parts of that sequence you can actually impact at the lowest cost with the most effectiveness. So the first stage of any optimization process is going to be to understand actually what you're doing. You can't optimize something if you can't describe it as a process. So that's just a first comment on optimization. The bulk of this session is going to be on technology for optimization, but I just want to go through a few things with you as well. What does success actually...
We want to see who we got in the room.
Yeah, we could do that, Tony. Yeah.
So, hands up if you're a driller.
We've got 2, 3 drillers, 4 drillers in the room. Okay.
Hands up if you're a geologist.
Okay, we go. And so,
Those of you who are not geologists and not drillers, what is some of your background? Tell us some of what your roles are.
Drilling engineer.
You're a drilling engineer. Good.
Yeah. That makes you a driller, really.
Yeah, you're a driller. Yeah.
Yeah.
Planning.
Planning? Okay. Planning. Yeah.
Have some more.
Developer.
Developer?
Developer.
Okay. Yeah.
A geothermal asset developer.
Geothermal power.
Okay. Yeah.
Company.
So this is all cost for you guys. This is just a huge amount of money, big checks that you keep giving, and you have nothing to show for it. You're just a small hole in the ground at surface.
That's the reason I'm here.
Yeah, yeah. 60 to 70% of your costs go in this. Yeah. So, okay. Any others? Any other disciplines that we've got in the room?
so what? EPC company
Okay.
or power plant?
Yes. So you're the power plant side of things. Power plant. Yeah.
Some of the others over here.
I manage the work site. I manage the work.
Cool.
You manage the work site
Okay.
for drilling or for anything.
At the moment,
Okay.
Yeah. Okay, so again, understanding the process is really helpful for coordination. So, yeah.
Yourself?
Developer also.
Developer as well.
Yeah.
Any more developers in the room?
Yeah.
Okay, good.
Okay, so we've got a good,
got a good
mix
spread.
of people.
Yeah.
Yeah, but
Almost
As-
no drillers.
exactly. Oh, we'd better run away. What does success actually look like for you guys in drilling terms? I mean, we could say, there we are, success. We've got a hole in the ground. Is that good enough? Maybe it would be more successful if we had a hole in the ground and we drilled it fast. Yeah? Is that better than just a hole in the ground? Or you don't like having to pay the money for the hole in the ground. Maybe you'd prefer this to be a hole in the ground that was drilled fast, but also cheaply. Is that success? Is that what that looks like? But first of all, what does this even mean? If we mean drilled fast, how do we define drill fast? We can look at a computer screen while we're drilling, and we can see a number on that computer screen. That computer screen might tell us we're drilling 100 meters an hour. But that's only for 1 second. Is that useful? Or maybe we're drilling 100 meters an hour. Is that for a period of an hour? Is that better? Or maybe over the last 12 hours, we've made 300 meters. Is that a better measure of how fast we're drilling? What about the daily ROP? Is it what we see on the daily drilling reports that actually matters? So all of these are definitions of how fast we drilled the well. We've got to make sure we understand what's actually meaningful and what isn't. What about the weekly ROP? Is that a better measure of how we're performing? The section ROP, we drilled a 12.25-inch section in 6 days. Is that better than understanding what our hourly ROP is? We've got to understand what the true key performance indicator is here. Or are we going to look at the entire well from surface to total depth and decide that that's what our metrics is for performance? What just popped up here? Does it matter if we've got good performance, we've got a cheap hole in the ground, if we broke the law to do it? Tony, do you want to go to prison for that well you just drilled?
No, Kevin, I would like to do it and stay out of jail. Thank you.
Oh, okay. So we're going to have to do it legally, okay? Oh, what was that? Tony, in 3-4 months' time, when we've left the rig site, the well's going to fail and we're going to have hot steam venting into the environment around the wellbore. Do you want that? We're not even going to be in the same country when that
Kevin,
happens.
I'd like the casing design to be good enough for us to not leak. Yeah.
Okay, so we'd better have some form of long-term well integrity. What does this even mean? Low tortuosity. What's that mean, Tony? What is tortuosity? Why am I interested in tortuosity? This is supposed to be a drilling optimization class.
What's tortuosity?
It's the degree of bending that you have within the well. You want to have a minimum tortuosity and the smoothest wellbore possible.
Okay, so we want to have the smoothest, straightest wellbore that we can drill. Why do we want a smooth, straight wellbore? We need a smooth, straight wellbore because a smooth, straight wellbore is first the straightest path that is capable of being drilled between where we are and where we want to be. And if we have low rugosity, which I think is on here in a moment, we have the smallest volume of rock to be removed from the well to create the well. So we're not wasting energy drilling rock unnecessarily just to have what we call gauge variation or rugosity. Does it matter if we get stuck with the drilling assembly? while we're drilling, is that going to impact our performance?
Drill string's going to cost us $1 million. We don't want to leave it in the hole.
Yeah, but Tony, I own that drill string, so if it costs $1 million, it's in my interests that we lose it in the well because we can charge these guys.
You don't work for Schlumberger anymore, Kevin.
Okay, oh sorry, no, that's true, that's true. Okay. We don't want to get stuck, so we need to design our well in such a way that we don't get stuck while we're drilling it. And actually, our low tortuosity, our good quality directional drilling, our good quality control of the wellbore quality is key to not getting stuck. This one I like. We've drilled the well. Tony and I are directional drillers at heart. We have drilled the well for you guys. We did it cheaply. We did it.
We've got a question.
Oh yes, go ahead. Okay, good question. It means rate of penetration. So when we're drilling, we define the speed of progress with the acronym, and a very good question, rate of penetration. That's how fast we're actually drilling. And my sincere apologies for leaving an acronym on the slide. It's such a common acronym in drilling. We often forget that people outside the industry wouldn't. So thank you for asking the question. That's brilliant. Okay, so Tony and I have drilled the wellbore, and you guys have completed the well. Tony and I were sitting on a beach in Bermuda somewhere, having a cocktail, we're enjoying ourselves. And you phone up and you say, thanks for drilling that well, guys. We put it on production, we did a production test. We were expecting immense flow rates. That's what the geologists told us we would get. We're getting nothing. Nothing at all.
So the geothermal developers in the room, you want us to drill you a well and then have no water coming out of that well?
Yeah. Yep, go ahead.
Many drilling companies in Taiwan use the mud drilling method, and how to calculate the computer.
Yes, absolutely. As we drill, we circulate a drilling fluid around the wellbore, and that drilling fluid is quite often called mud. The component parts of that mud have to be compatible with the permeability and the porosity in your formation. They also have to be, the mud base fluid has to be chemically compatible with the formation fluids, because if you don't have that compatibility, we can actually destroy the near wellbore permeability as we drill the well. And anybody that's seen any of my posts on LinkedIn know that I quite often can't hold back when I see a project and they say we're having to sidetrack because we've got no production. And we blame the geology team for that. And I look at the project, I look at what they've used, and I say, there's nothing wrong with your geology. You destroyed the permeability of your well while you were drilling it. We have to have a strategy in place to protect the permeability of the reservoir section from our drilling process. So there's no point having a fast, cheaply drilled well if when we actually put it on production, we're not getting the flow rates that we anticipated. In the oil and gas industry, we'd call that creating a high skin factor. So this principle of creating a low permeability skin around the wellbore is critical to the actual project success. It's not directly going to impact how fast we drill the well or how cheaply we drill the well, although we could argue that the cost of a more robust drilling fluid is potentially higher. Yes. Yeah.
I would say in hydrothermal systems, it's less of an issue, the skin. Normally you hit into fractures, and sometimes the only way to drill this well to PE
is with complete losses.
And actually what you're doing is all the cuttings are going to the fracture. So this is depends on the well type. You're completely correct. If we are in a hydrothermal system that relies on permeability of the base rock rather than fracture permeability, although we can destroy fracture permeability as well with drilling process, especially when we're drilling with complete losses. When we're drilling with total losses,
which means we can't get the circulated fluid back to surface. We put all of those drilled cuttings into the near wellbore fractures. We can substantially reduce the permeabilities. Rugosity. Does anybody know what the term rugosity means?
Bumpiness.
Bumpiness, absolutely. Is the well smooth, or does it change diameter repeatedly as we're drilling? Where does rugosity come from? I'm picking on you. I'm sorry. What? Oh yeah, you're a. Oh, sorry. It says attendee. Yeah. Why do we get gauge variation in drilling?
You kind of depend on the degree of interbeddedness, how interbedded the formation is. That's one key factor. The other is if you're drilling the well in the wrong way, as far as leaving ledges or having that rugosity via not stabilizing correctly the wellbore, you might get rugosity.
You used a special word there which begins with S. What was that word again? Stabilization.
Yeah.
Okay.
So geomechanics and stress comes into play.
Yeah. So when we're choosing our drill bit, when we're designing our drilling assembly, and when we're planning our well, there are lots of things that come together. We can drill in a formation that is unstable geomechanically, and unless we understand the geomechanics of that wellbore, we're not going to have a cylindrical wellbore. If we have a stable formation, we can still drill a rugose wellbore if I put a drilling assembly and a drilling bit in the well that is not stable. That drilling assembly is going to vibrate. We're going to have rugosity created either by natural geological process of stress imbalance around the wellbore, or we're going to have an induced rugosity due to shock and vibration occurring in the drilling equipment. So we've got to make sure that we understand we've got to control those things. Good T and D. Does anybody know what T and D stands for? Torque and drag. As we drill a good quality wellbore with a nice mud that's got good lubricant properties, it'll be very easy to slide the drilling assembly in and out of the hole. We'll have a lot easier time of our drilling operation. But when we've finished drilling, we need to run something else in the wellbore. We need to run the casing string in the wellbore. And if we've got poor quality hole, we've got lots of rugosity, we've got poor torque and drag figures, our casing string will not go in the hole easily, and we can easily waste long periods of time struggling to get our casing string into the well because we didn't look after torque and drag. We didn't look after torque and drag because we didn't look after our tortuosity, we didn't look after our rugosity. Nobody wants data. I've never drilled a well where people want data from it. We're putting formation evaluation tools into the wellbore. We're spending a lot of money to put those formation evaluation tools into the well. Do we want good data from them? Absolutely. If we have a drilling assembly that is subject to shock and vibration, we're not going to get good data from that tool. If we've got a wellbore that's got high rugosity, so the gauge varies all the time, all our assumptions about our corrections for the data collection, for the mud distance, the mud thickness, are going to be wrong. And we're not going to get a good data set. And what's the impact of not getting good data? We don't understand the reservoir properly. And if we don't understand the reservoir properly, we're not going to be able to manage it properly over its life. So,
and what are some of the things that we want to know, particularly in a geothermal well? What's one of the most important data points here?
Temperature.
Temperature, exactly. Yeah. We want to know what that temperature gradient is down the wellbore, so that we can at least then start to do our calculations on what we want to get out of the well. So there are plenty of tools that can measure the temperature in the borehole while drilling. But there's impact on that temperature because we're pumping cold fluid down there and we're circulating that back up to the surface. But we want to see how that temperature is changing in the borehole.
The most important data point for me is my salary check at the end of the month. Is that not good? No.
What's another thing we want to know? So if we're drilling a hole in the ground, what else do we want to know about that hole?
Flow rate.
Flow rate, yeah, absolutely, yeah. Flow rate coming out of the well and the flow rate that we're putting in to drill. Yeah. What happens if we've got two wells close together? What do we want to know about those two wells? Interference, yeah. And we want to know where they are, yeah.
So we don't run into them.
So we don't run into them. So we will run MWD, measurement while drilling tools, that measure the inclination of the hole and the direction of the hole, and then we measure that back to the surface so that we know exactly where the wellbore is. So we either connect them together because we want to connect them together, or we keep them well apart because we want to keep them well apart. So,
yeah, cool, excellent. So all of these things, or a lot of these things, come down to the design and selection of the equipment that we put into the wellbore to actually drill the well. We need to make sure that as we drill the well, we do so without the drilling assembly vibrating and impacting with the borehole wall. Because not only does that massively impact the quality of the wellbore that we create, it's going to impact how fast we can drill. Because if I'm putting energy in at surface in terms of RPM, weight on bit, hydraulics, I want all of that energy to go to the drill bit and destroy the rock. Any time we spend energy vibrating the drill string, bending the drill collars, we're not using that to destroy the rock. Our rate of penetration will start to drop. Okay? Tony? Yes. Tony, I've got a problem. There's lots of fluid coming out the top of the well.
Are you steam cleaning the rig again, Kevin?
Yeah, I'm really pleased this isn't an oil and gas well, because it would be on LinkedIn. Somebody had posted a video of it on LinkedIn and it would have probably caught fire. But there's lots of fluid coming out at surface and I can't stop it. Is that a problem?
Yes, please, Kevin. We need to fix that.
Okay, so as we drill the well, we need to keep the formation fluids in the formation while we are drilling. When we go to production, we want the biggest flow rates to surface, but we don't want that to happen while we're drilling, because if it happens while we're drilling, we can't continue to drill. We're going to have to stop and control that uncontrolled flow from the formation. And that uncontrolled flow might not be from our reservoir, it might be from a shallower formation that might contain methane. Methane is a problem because it might catch fire. Okay, so we need to make sure that we design our well in such a way as to keep the formation fluids and gases in the formation while we're actually drilling the well. You know, I said we should buy that really expensive mud, Tony?
Oh, you've got no mud losses? Yeah. This is a geothermal well. I want to lose all my mud in the well.
Yeah, that's the problem. I've just told the client to buy a really expensive, good quality mud with good lubricant properties. It's not going to create a skin, but we've lost it all. It's all disappeared down the well. We're not getting any returns. So you're paying hundreds, if not hundreds of thousands of dollars for your mud, and it's all disappearing into fractures in the well. We need to try wherever possible to design the well and design the drilling process to maintain the mud in the wellbore as we are drilling.
But you may not be able to avoid losses.
Yeah.
So if you can't avoid the losses, you want to make sure that you have enough storage of fluid that you can pump down the hole to be able to keep drilling. So you need a big pit or a big area that you've dug out and covered with plastic to store very low cost fluid, which is typically water with some cheap additives in it.
Yeah.
Shallow losses are so common when we drill. Is there a reason to use a different mud in the top hole
Yes.
than the bottom hole?
Yeah. We would typically, we might even have 3 different mud types in a good well design. What we mustn't do in our shallow formations is we mustn't risk contaminating the shallow aquifers, because the shallow aquifers are potentially where we're getting water supply from for the cities and agriculture and things like that. Then once we've actually successfully cased and isolated the shallow aquifers, we're going to use a fluid that is most cost effective to drill the bulk of the wellbore. But just before we get to that precious reservoir section, what we might consider doing is displacing all of that mud out of the well, because it's going to be contaminated with drilled solids, what we call low gravity solids from the previous sections. It may have actually been selected on price alone to be the most cost effective fluid for the long drilling section. But before we get into the reservoir, we might want to displace that mud out and get rid of the chemicals that we've used to create the mud properties. Things like bentonite. Bentonite is a very, very cheap viscosifier, fluid viscosifier, but it's not very good if you squeeze that bentonite viscosified mud into the permeability of your reservoir. It's going to damage the permeability. If we're using a weighted mud system, which isn't that common, but there are situations where we do, if we're using barite, which is the most common mineral for creating density in our fluid, and that goes into our formation in the reservoir section, we can't get rid of it afterwards. We could change the weighting material to calcium carbonate, and then at least we can acid clean the formation in the reservoir. So our mud system is critical to success. Tony, we've managed to drill the well with all of these criteria, absolutely fantastic, but I lost one of my legs while we were doing it because I wasn't very good on the rig floor. Is that a good success?
No, safety is going to be of utmost importance for these projects, yeah?
Yeah.
So you want every single person to go out for that rig, come back from that rig, and be safe and not hurt people.
Yeah, and this is interesting, because as we travel around the world, there are 2 different areas that the drilling people come from. We've got people who are ex-oil and gas drillers, who are used to drilling under oil and gas safety regimes, and they are typically compliant with all the safety procedures. We've also got a subset of drillers globally that come from geotechnical or water well drilling industry. What we've found is that the geotechnical drillers and the water well drillers, their compliance with safety is not as good as the oil well drilling fraternity. So we're going to have to manage our HSE process. Already mentioned, we don't want to damage the aquifer, because if the project is successful but nobody in Taipei can drink any of the water anymore, that's not a successful project. Tony, we've got to the right depth, but we're in the wrong place. Is that okay?
That is not okay.
Okay.
And shall I tell them a little story?
Yeah, yeah.
Yeah. So
is it a young, handsome directional driller?
Young, handsome directional driller called Tony.
So, we don't know who that is, by the way. It could be anybody.
So I was drilling in the Gulf of Mexico, and when you design these wells, you have to put in the compass bearing of the well, and when you put that data into the computer, the data has to have the magnetic correction for your location on the planet. I was from Scotland, so I was used to that number always being negative, minus 2.5. The directional drillers with me on the rig were from Alaska. They were used to a negative number. So when the computer gave us 2.5, we put 2.5 in the computer as minus 2.5. So what we drilled for a month was a well that did this, but it was meant to do this. the oil was here, and Tony's well was over here. It cost Chevron $12 million to put it back in the right place. So a year later, I heard on a radio show, you could ring in and explain your most expensive mistake. And for 2 hours on the radio show, I was in first place. And at the end of the show, I was in second place because an army captain had driven a $26 million tank off a cliff and smashed it. So he won the award.
Yeah.
The point we're making, though, is there will be lots of very important parts of this process that professionals have to do, and then the management system has to check what they're doing so that mistakes don't happen. Because you, as a geothermal developer, want that well to go through those faults, go to that place that you expect it to go to, so that you get the production that you want. So process, which is, as Kevin started, is there should have been something protecting me and the others from making that mistake.
Do you know the honest truth? Although Tony's always very honest about his mistakes, and I'm usually very honest about mine, I say usually. It wasn't the first time that had happened in the same company. It happens many, many times round the world every year. People make mistakes with the position of the well, the corrections to the surveys. It is a repeated mistake that the industry is very familiar with. So we need to have a process in our operation that makes sure that we catch these mistakes before they cost 12 million. I've never made that mistake. I've honestly never put the wrong correction. Sorry, Tony. No. Yes, I have. Okay. What else do we have to think about? Low NPT and ILT.
You've got acronyms again there.
Yeah. What are those? What's NPT?
Anyone in the room know what NPT? Non-productive time.
Non-productive time. So we should be drilling today, but the rig broke down. That's non-productive time.
So someone other than Greg, what's what's ILT? Invisible lost time.
Yeah.
Which one of those normally costs us the most? ILT, the invisible lost time, So invisible lost time is if I have this drill bit and this rock I'm going to drill, the theoretical speed that I could drill that is, say, 100 meters per hour. If you took the physics mass of breaking that rock 100 meters per hour, but we only drill it at 20 meters per hour for 50 days, all that invisible lost time, the difference between the theoretical speed we could do and what we are actually doing, is costing us millions of dollars. So it's very important to understand non-productive time. That's when we're stopped because we have a broken piece of equipment. And then the invisible lost time, which is the difference between what we could do and what we are doing. And that, if we can remove that invisible lost time with an optimization process, we will get faster and faster and improve the economics of our project.
Yeah. We've got a client who is drilling some wells, Tony. They're drilling the wells in hard rock, and they've decided that they're going to go to our colleagues here at Reed Hycalog, and they're going to buy some drill bits. They're going to buy roller cone drill bits, Tony.
Reed Hycalog don't have any roller cones.
Don't they?
Yeah, okay.
Yeah, that's fine. So they're going to choose a bit technology that is an old bit technology because they believe the individual pieces of equipment are cheaper. They're going to spend 38 bit runs to drill their well. I'm not making that figure up, by the way. That is a genuine client in the south of England. Spent 38 bit runs to drill their well. We could have gone to Reed Hycalog or any of the other vendors. Sorry, I'm just picking on Reed Hycalog because we've got a victim in the front row. We could have gone and said, what's your latest bit and cutter technology for drilling this type of rock? And they're going to come back and say, we're drilling 125 feet an hour in hard granite in the USA. We could have drilled that client's well in 5 to 7 days, not 38-bit runs in 3 months. The client thinks that they were productive. They think they were productive because there was no non-productive time or very low levels of non-productive time. But most of their operation was invisible lost time because it wasn't actually drilling effectively. Okay?
And not only that, Kevin, but you increase safety risk by doing more connections.
More safety risk, you've got more risk to the formation as well. You've got more risk to your permeability. You've got more risk in general. And your costs are huge as well.
And it's a simple question. It is, what is the difference between cost
and value?
So,
yeah, but at the same time, it doesn't mean that every rock is PDC drillable, right?
Every rock is PDC. Every rock is PDC drillable. Every rock is PDC drillable. No, it's not. Absolutely not open for debate anymore. You're 18 months ago. 2 years ago, absolutely. Every rock is now PDC drillable. New cutter technologies are actually able to drill all the rocks that we used to say had to be roller cone bits, and we've got to move away from this mindset, I'm afraid, that we have to use roller cone bits because of certain rock types. 18 months ago, 2 years ago, absolutely the right statement, but we have moved on so much.
You're talking maybe in terms of ETS or some of the geothermal environments, but there are environments where we haven't been able to drill the PDC yet.
What technologies have you used?
I mean, we don't need to get into the details. I'm just trying.
We do need to. This is really, really important. It's really important because
it's a very good challenge. Yeah.
Yeah.
I wouldn't put it as 100% PDC.
I would absolutely, and that's from all of the bit manufacturers. We really need to move away from this perception
that we're getting there, but I'm just trying to tell you that there are environments where we haven't been able to crack the code with PDC yet.
But you just gave us the perfect answer. So the gentleman challenged Kevin and I.
And thank you for that. By the way, we value the kickback.
We made a sweeping statement, which are often dangerous, and we said that every rock is PDC drillable.
What is a PDC, guys? Just a quick question. Everybody know what a PDC is?
We have some pictures coming up in a minute.
Yeah.
But we can explain it. So drill bits have, there are 3 main types. We have roller cones. So roller cone bits have 3 cones with teeth in them and 3 cones on the bottom that roll like wheels. Yeah. And inside of those cones they have either cut steel or tungsten carbide buttons that hammer the rock. So as it rolls around the hole, we've got some pictures coming up in a minute anyway, it rolls around the hole and it hammers the bottom of the rock, and the rock breaks up. We then have PDC bits, and the PDC stands for polycrystalline diamond compact. They are discs of diamond. So what has happened in just a very short period of time, PDCs have been around since I joined the
50 years this year.
A long time, yeah, 34 years, and some people in this room are probably younger than my career. Those PDCs have been around.
You don't look that age.
But what has changed in the very, very recent time, and it's Reed Hycalog, Alexis is here from Reed Hycalog, Anne's here from Schlumberger, so Smith is a Schlumberger manufacturer, Baker Hughes, Altera, there are different bit companies, but all of us have had a jump in performance. And that jump in performance has come from the pressure that we make diamond at. So diamond pressing has become so effective that we now make diamond 4 times thicker than we did only 3 years ago.
And with much lower levels of a metal called cobalt in the cutter, which is very important because let's go back to this statement here. If you can't describe what you're doing as a process, you don't know what you're doing. Selecting a drill bit and using that drill bit is a process. It's not just about picking the drill bit. It's about how you use it in the well. And our understanding of how to drill efficiently with PDC bits without damaging them and destroying them isn't just about selecting the drill bit. And the way we used to select drill bits for PDC selection for hard rock is very different to how we select them now. We've completely changed our PDC selection process. Yeah.
One thing. To Hans' point, there are highly fractured volcanic formations that haven't been able to be drilled with PDCs probably since a couple of years ago. In Iceland, we see formations that are highly fractured, basalts and some igneous rocks and volcanic rocks are highly fractured. The only attempts that have been done with PDCs have fell in their face because the cutting structure fails prematurely. If we find the right cutter grade for those formations, you may be able to drill those effectively, because in the last couple of years we've advanced the technologies for impact resistance and thermal resistance so much that 100% of the rocks can be drilled with PDCs. We just need to make the test, and there are some people that are fearing not to use them because they failed in the past, but when they say in the past is a couple of years ago. Right now, today, the technology has grown so quickly that you can drill with PDC.
And the gentleman actually said the exact answer. We haven't cracked the secret sauce.
Yeah.
So
absolutely.
So from a physics point of view, we believe every rock is drillable with PDC. But he's absolutely correct in today, the secret sauce for some of those rocks has not been solved. And to be honest, one of the things I've been working on a big research project for the last 4 months. One of the potential solutions to that is combining some technologies from 2 different bit companies, and it is a very interesting combination. And one of the bit companies have a bit that has roller cones and PDCs in it, and so they combine the 2. But we really believe now PDC, which shears rock, doesn't hammer it, has the potential of drilling all rock. But we will talk as we get later on today, and those of you coming to the class tomorrow and Friday, we will talk about not only is the product important, but how you treat it.
Yeah.
So many of the failures with drill bits have been that people have not followed a process to run that properly. And often people think the best way to put a drill bit on the bottom of the hole is gently. That's completely wrong. If we put it on gently, the shape of a drill bit, hold that for me.
Yeah. So just as Tony's drawing his drill bit there, a lot of our legacy process, our legacy understanding comes from older technologies that are no longer relevant. How we control shock and vibration at the drill site, how we go on and off bottom, how we actually design the bottom hole assembly to give us the weight on bit. We're looking at weight on bits that are 4 to 5 times what we traditionally used to run on PDC bits. And that means a complete redesign of the bottom hole assembly, the equipment in the well that's actually going to give us the weight on bit. So our drilling process has changed massively as well. Sorry, Tony.
So this is our drill bit with our polycrystalline diamond cutters on it. And if we put it down on bottom gently, and everyone's going, oh, Mr. Driller, be careful, put it on gently. It does this, it vibrates. And when it vibrates, those cutters that would cut the rock get impact damage. If we put it on steady and increase the weight really quickly, this piece of rock in the middle forms a cone and stabilizes that bit. So even though it's got aggressive parameters on it, it becomes stable in milliseconds. And then we carry on using it, we cut the rock steadily. Then when we get to the end, and we've drilled 30 meters, we have to pick it up quickly as well. And there was an old myth in drilling called, oh, let the let the bit drill off, which what that meant is you drilled the 30 meters and then you just waited, and all the weight in the drill string slowly drilled off. And what happened in reality, as it drilled off, it went into vibration and we damaged the bit.
Yeah.
So the bit wasn't being damaged when we were cutting rock. The bit was being damaged going on bottom and coming off bottom. And these little small things make a very big difference to what you do. Yeah.
And traditionally, if we had interbedded hard and soft formations, we'd drill very aggressively and fast in the softer formations, and then we'd try and baby the drill bit through the harder formations. Yeah, we've got
one more thought.
There are some instances where it is not economical to drill with PDC, so boulders in surface are drilled with roller cones, and you're always going to be needing roller cones as a contingency. And also, if you have coring sections in between, there might be more economically feasible to run a roller cone in the short sections. But normally, the way is to pick up PDC bit.
Yeah.
Absolutely. So we, where was I before? I can't remember. Never mind. We're going through hard and soft formations. We would typically be very gentle on the parameters going through the harder formation because we thought the formation itself was going to damage the drill bit. It's not, it's the vibration that damages the drill bit. So we've completely changed our way of drilling hard interbedded formations, fractured formations. We're actually being massively aggressive now with the weight on bit, to the point where we're pushing the weights on bit, on PDC bits, to the structural limit of the blades of the drill bit. That's the limiting factor for weight on bit, no longer the cutters. And we're typically going to less blades. We're typically going to bigger cutters. Bigger cutters are stronger. In the past, for hard rock drilling, the traditional approach was to put more blades on, put smaller cutters. No, we're going less blades, bigger cutters, better quality cutters. So that's a huge explanation of ILT, which is just one aspect of things. But let's keep going. Oh, we missed one here. Tony, we successfully drilled the well, but everybody around us hates the project. There are protest groups, there are people telling us that Kev drilling and pink drilling, they're the worst thing on the planet. It's on the news. They hate us.
And we talked about this, those of you in the big room yesterday, the panel session at the end, about how everybody in this room who's going to be doing geothermal energy in Taiwan, how we want to make everybody else in the country think positively about geothermal energy. And geothermal energy is so positive. You know, it's a green energy, it's baseload. It is loving the planet that we live on and taking that nuclear reactor that is below our feet. We're creating nuclear power with no waste.
Yeah.
You know, it's just using our Earth's nuclear. So how you manage your communities. Another funny story is the toughest community you will ever explain geothermal energy to is your parents and your parents' friends. Yeah. So my father invited me to a meeting of all the elder people in the town that they live in, and I did a presentation on geothermal. I created 1,000 geothermal activists who then went and told all their other old people that geothermal energy is really good. Yeah. And now I'm getting bugged the other way. Why don't we have a geothermal well in our village?
Yeah, so, absolutely.
So that social acceptability, it's about creating warmth or creating cool or creating clean energy. You know, that story is very, very important.
And actually, I would go a step beyond that. And this is from France. I live in two locations. I live in the UK and I live in the south of France. It's a long story, but we'll not go there. I know it's tough. But they're desperately trying to get me to join the Rotary Club in France. The Rotary Club are desperate for us to go and talk about geothermal energy. And these organizations, Rotary Club, Lions International, are global organizations, and they talk to each other. it's an amazingly effective way of getting your message out there. Go to the organizations like Rotary, like Lions International, Toastmasters, things like that. Those guys have a huge influence. So absolutely, we have to be socially acceptable.
That follows on, really.
Yeah, I think environmental compatibility is important.
As drillers, you know, we often are associated with dirty, greasy, oily, noisy. When we do our drilling operation, especially in Taiwan, it's a country with a lot of people, small country. Same in
it's
England.
Amazingly clean and pristine, guys. It's a lovely place.
England is the same. It's a very small country with a lot of people as well. So
not as clean.
We want we want our rig to look green. We want to, if possible, plug it into overhead power. We want to make a smaller footprint, and then when we leave the location, and all that's left is a wellhead, and then we put the grass back and we make it look clean. We have a tiny footprint, so it is very important for our industry, for the people to understand that we will put a big rig there for a bit, but it'll be gone and it'll be back to normal afterwards. And there'll be less footprint than a power station, and so we'll have a tiny little bank of fans and coolers. That message has to come out. But as drillers, we have to be very sensitive to how people feel about us while we're drilling. And it's best to get people around and have tours and explain what you're doing. And it's lack of knowledge makes people afraid. Yeah. So
if I can just interrupt for a second,
you
may know Roy Barria, who is
an EGS proponent from donkey's years, right, from a long time ago, and he was doing the quarry at Rosemanow's a long time ago in Cornwall, which you mentioned yesterday. And he decided to, as an outreach activity to the community, to capture the sound of the fracturing of the rock at depth. And so using geophones and stuff like that. And then he had some speakers, and he played it, and he said this was rock music. Yeah. So it was one of those things that sounds really crazy, but it actually, the public was very into it. And they said, okay, when's the next time we're going to hear our rock music? Yeah. So he made something that could be a negative into a feature, which I thought was brilliant.
Absolutely. And to go a stage further for that that same project and that same location, the guys, because of availability of rigs, they had to select an oil and gas rig, a tall, very high, very noisy rig with what we call a drawworks hoisting system. So it's oil and gas technology, not really fit for purpose for geothermal. We're looking at better rigs, better designs for geothermal. What did they do? They put a skull and crossbones flag on the top of the mast, and they are the geothermal pirates. They are, and the community, the work they did with the community there. If you go to Cornwall, everybody in Cornwall that I speak to, oh, are you involved with geothermal? Oh, fantastic. And whilst that's not drilling optimization, it's project success, which is really, really important. Yeah.
Crack on then, Kev.
Yeah. So, just a couple of final statements. Understand your project's key drivers. Before we can do any optimization, selection of technology, we've got to understand what your project key drivers are. And I'm going to ask this question. Do you have a company drilling policy in place? No. Almost all of our clients go, company drilling policy, what's that? Company drilling policies are absolutely crucial to actually defining what our well designs are going to be. That's how we inform our well design. And do you have company drilling guidelines in place? Because when we write our drilling program, Our drilling program comes from the well design that's informed from the drilling policy and is created in association with the drilling guidelines. So there's a very clear process we must go through in order to have a competent well design and a competent drilling program. So here we start with the company drilling policy. It informs the well design. We use our company drilling guidelines to take that well design and create a drilling program. That's how we should create a drilling program for our well. Now, most geothermal operators that we're working with at the moment, they're not ex-oil and gas. They're not used to having these documents or these processes in place. So once we've created the drilling program, Tony, I finished last night about 3 o'clock in the morning. I finished writing the drilling program. Should we just send it to the rig, or do you want to get somebody else to look at it? I'd had a few drinks when I'd finished it, you know.
I think we need a little bit of a thorough audit process on that, Kevin.
Okay, so first of all, I'm going to give that drilling program to somebody else in my own organization, and I'm going to get them to go through and sense check it. But I'm also going to go, Tony, are you available for consulting services to look at my drilling program and say whether okay. Yeah. Pink Granite Consulting, great company. We can take that to Tony. So we can have that external peer review of somebody who doesn't know every detail of your project, so has a wider picture, is going to look and go, hang on a minute, you've forgotten this, or why are you doing this? Oh, you're doing that for that reason. Okay, that makes sense. They're going to question you, and a peer review process, going back probably 30 years now, I was in a peer review for an oil and gas well where the guy that had written the drilling program, the senior drilling engineer, almost had a fist fight with the guy who was doing the peer review. And it became really contentious. That's not how it should work. It should be a critical process, but it should be a constructively critical process. It shouldn't descend into personal abuse. So once we've done that external peer review and we've sent the drilling program back for revision, we are happy between our internal experts and our external expert that this is the best drilling program we can have. We're then going to do a thing called a drill the well on paper exercise.
And that's such an important process to drive everybody that's going to be involved in your project to be part of it. So what you do just before you start to drill, you get everyone in a room like this, all the people that wrote the different components to your program, and then you do an exercise where you do it on paper. So you say, we're going to drill the first hole section, and you get everybody in the room to put their input in the, and then you'll find that one person in the room goes, oh, I didn't realize that you need that, and you find a little mistake that could have cost you invisible lost time or NPT, and you do it all together, but you get an extra benefit. You get a great team atmosphere by doing that exercise together.
Yeah, these two internal peer reviews typically will pick up technical or mathematical mistakes, cut and paste mistakes, technical things. The drill the well on paper usually picks up procedural mistakes or things. We've been in a peer review where we were looking at a mud displacement from the well, displacing to another mud type, and the internal peer review hadn't picked it up, the external peer review hadn't picked it up. And then the derrickman that was in the drill the well on paper said, I'm just reading this displacement. There's no way, because he was Scottish, there's no way it's going to be possible on the rig that we're going to be using. It's not possible because we don't have a line that connects those two tanks together. You can't do what you think you're going to do. And although it cost us a few drinks in the bar afterwards for the drill well on paper, it probably saved us 3 or 4 days of rig time. So this is the process by which we create a competent drilling program and we create good quality daily drilling instructions. Okay, In a longer course, we then talk about what we call a RACI matrix, so an accountability matrix, and smart instructions at that point. But if I keep talking, Tony's going to beat me up. So,
can I just ask you one thing about this? It's I think the all of this is excellent and what is normally done in geothermal, I would say, but the rig itself, you brought up a point that the Derrickman raised, and I think the rig itself may not be able to follow that program. So is that fairly common, or is it, is it best to really know your rig?
I think, sorry.
Yeah, go ahead.
Just for the recording.
Yeah.
I think the longer that you have a rig on location, the more wells you drill, the less likely there are going to be these little problems at the DWOP stage, the drill the well on paper stage. But for a client who's picking up a rig for the first time, and sometimes the rig selection, we need a well design before we can even specify the rig. We need to know what the well design is, and to an extent, because of the shortage globally of suitable rigs for our project, it might be this point or even this point at which we actually get a rig contract in place. So at that point, this DWOP is extremely valuable, but the longer you have the rig on contract, the more wells you drill, the longer the client has embedded this process, the less likely that's to happen.
Who in the room is from CPC? CPC employee? How many rigs do we have in Taiwan at the moment?
Right now we've got 2 available, but we purchased 3 new rigs.
So 3 new rigs coming?
Yeah. Yes.
But you have how many in the country working today?
2 drilling.
2 yeah. So if this geothermal activity, which we're all excited about, goes crazy, you're going to have a decision where you go, what rig am I going to get? The only one that's left. Yeah. So it is very important that we understand the limitations of that rig, and how we can get the best out of it. But in the well design process, rig sizing is the phrase that is used around the world, is very, very important. We have to be able to have a rig that's strong enough to pull everything out of the hole. It has to be powerful enough to turn the PDC bit, because, as the gentleman said here, the roller cone bit may be the only choice we have, not because the PDC can't drill the rock, but because the rig can't turn the PDC. So it's very important that we think about this whole system.
Yeah. So oh, sorry.
So, regarding the environment issue that you mentioned before, is it feasible to have an electronic rig? I mean, totally electronic, rather than using diesels, or I don't know.
So there are rigs being built today that run off mains overhead line power. So you can plug the rig into the power grid and run that without any diesel generators. And there's also lots of green processes going where every time you lower the pipe into the hole, it spins up a giant flywheel that stores energy in batteries, so that when you pull, it can take that energy, so that the use of the energy use of the rig drops down as well. So there's lots of green processes going in. They can inject hydrogen into the diesel generators, so they burn less diesel. So, good question. As Taiwanese people start to develop a fleet of rigs to do your geothermal work, is go out there and find some of those environmentally friendly rigs out there, because you're starting from fresh. Yeah.
For those green rigs, are they it's like power enough? I mean, strong enough to do the work?
With the overhead power, yeah, absolutely.
Yeah, absolutely. Yeah. One of the projects Tony and I are busy working on at the moment is with some of the rig manufacturers to specify exactly what it is that we want for rigs that are fit for purpose for geothermal. Especially for urban heat-related geothermal. You don't really want a traditional drawworks oil and gas rig. Your footprint is limited. The amount of space we've got is limited. We don't want noisy equipment. We want absolute silent equipment. We don't want diesel generation because that creates emissions and noise. So there are lots of little details on rig design for fit-for-purpose geothermal operations. But it does depend where you are. If you're drilling in Cornwall, in the quarry in Cornwall, you can hide a big rig in there. Nobody's going to see it because it's in a quarry, it's in a hole in the ground. So you can use traditional oil and gas technology, but actually as a geothermal industry, as we take off, we need rigs that are fit for purpose for our operations. And to go back to the drill bit question, in order to run some of these new PDC bits, our BHA design, our bottom hole assembly design is very different. We're using collar diameters, big collar diameters that most smaller rigs can't handle. So we're going to be specifying 9 5/8 inch or 11 1/4 inch collars that most smaller land rigs just cannot handle. But we need them to drive the new generation of PDC technology to drill effectively. So, yeah, cool. Okay, just one final comment from my section of this, which I've overrun a few minutes, Tony, I do apologize. You must own the drilling process. As an operator for geothermal, you have to own the drilling process if you're going to do it efficiently. You cannot just assume that your rig contractor will take care of everything. Your rig contractor is probably on a day rate. They like to have a long drilling process because they make more money. Sorry, did I say that out loud? I didn't mean to say that. Okay. Thank you, Tony. I'll hand over to Tony. There was a question over there, by the way. Sorry.
Yeah, I have to ask this before I forgot.
Yeah.
Yep. So the higher weight long bit for the PDC, does it apply to like off-the-shelf PDCs, or it applies only to the... Right,
so the newer generation of PDC bits, where typically we're not buying PDCs off the shelf anymore. We're looking at the geology, the individual lithologies that we're going to drill. We're doing cutter testing against those lithologies, so we're selecting cutters that match the lithology, because we've got a whole range of different three-dimensional cutters, from Schlumberger's Stinger technology to...
It's simpler than that.
Is it?
Work with your drill bit vendor.
Yeah.
So as directional drillers, which Kevin and I both were originally, we were very arrogant that we used to think that we knew a lot about drill bits.
We don't.
Then I joined a drill bit company, and I realized I knew nothing about drill bits. Yeah, so it's very important. Drill bits are a unique technology that every drill bit should be customized for the rock that you're going to drill, and the rig that you have to drive that bit. So you work with your drill bit vendor to come up with and every drill bit vendor will give you a proper plan of what bit you should run and how you should run it.
Yeah, I've been, because I stayed with Schlumberger slightly longer than Tony, I lived through 2 generations of bit vendors that were Schlumberger bit vendors. Originally, we owned, I still say we about Schlumberger. It's the chip in the back of my head hurts. We used to own Reed Hycalog, so I worked with the Reed Hycalog guys when we introduced rotary steering, and then they sold Reed Hycalog and bought Smith, and I saw 2 very different approaches to drill bit technology. But I believe that our drill bit expert has a little word to say at the moment.
Thanks, Kevin. Yeah, it's a good point you bring in. So the structural limit of the bits are normally much higher than the ones that are published in the tech spec sheets. For instance, in 9.5 hole section where Tony and I were running the bits in Forge, the spec sheet said 45,000 pounds for a 9.5 bit, but we put 70,000 pounds. So it's working with the drill bit company and making sure that the parameters are refined, and by doing that, then you increase ROP without risking the structural limit of the bit.
Cool. Yeah, carry on.
Yep.
You mentioned that
By the way, it said interactive on the
You mentioned that picking the drilling bits will be really depending on the lithology or the rock property.
Yeah.
Does it make any sense that because coring, I mean, owning a little coring rig is pretty cheap? Does it make any sense that we do the coring first, like drilling for like 2,000 meters or whatever, then we know the hole property?
Very, very interesting, yeah. So we're actually working on a project that we just went to help them, because in their mind they said, oh, we're now switching to the big rig, because they've been coring for the last 2 years, yeah. So they were doing lots of exploration wells using the core rig. Coring rigs are very good for you to understand the true geology that you're doing. You can core all the way down, and these coring rigs typically drill maximum 30 meter sections, and then they have to pull out. But you get incredible amount of data. You drill very slowly, yeah, because it's a diamond core head. It's not PDC. It's little tiny diamonds, and they will grind away, so you get lots of core out. But on an exploration program, a coring rig and drilling cores may be the cost-effective way to start. Then you switch over to deliver the holes that are going to produce your geothermal energy. It's not about just data, it's about now producing the right hole to produce the right fluids. So rather than going into a huge drill, we're going to start from the bottom up, and you're going to go, how much flow do I need out of this hole? And you start with that, and then you telescope back to the surface to do all protect the surface aquifer, protect the stability of the hole. But yeah, coring rigs can be perfectly adequate for what you're doing for exploration.
Yeah, and actually the project that Tony's talking about, they've got 2,500 meters of core pretty much from surface to TD, and we're working right now on drill bit selection. And actually the drill bit vendor companies, we said, no, we don't want just a generic recommendation. You're going to come in and you're going to sit in the core store, and you're going to go through and you're going to select sections of core. You're going to take them away to the lab. We're going to do cutter testing. That is optimizing your drill bit selection process. So if you've already got an exploration program where you're going to be coring, involve your drill bit companies at that stage, and they can start the cutter selection process early, because the beauty of off-the-shelf drill bit selection is that, can I have a bit? Yeah, oh, there's one coming tomorrow. We'll expedite it on the next flight. But that's not going to be fit for purpose necessarily. And I take the point, it may work, it may be adequate, but it's not going to be the optimum bit choice. So we've really got to take this to another level. But I'm now quarter of an hour over, so
we wanted it to be interactive. So let's change a little bit, and what we're going to try and do in the last 45 minutes is just have a look, give you a brief introduction. You know, that's all we can do in the time, of the technologies that are coming out in the world to make Taiwan start up here rather than down here. Yeah, we want you to be able to get access to everything, every mistake that I've made, every mistake that Anne's made, the geothermal community, she's never made a mistake in her life. Yeah? No. What have we learned in this ecosystem? Yeah. So just to go through the ecosystem, because what is going to be most relevant in Taiwan probably. You're going to be drilling some conventional geothermal for sure. Yeah. So you're going to drill wells. You're going to drill them down. You're going to intercept with formations that have fractures and cracks in them, and you're going to produce deep hydrothermal fluids from deep in the country. Going to turn that into, it's either going to be hot water that comes back to the surface, go through an organic Rankine cycle plant, and you're going to make electricity, or it's going to come back as steam and it's going to go through a turbine and we're going to make more electricity. And as you get more and more confident and you have success, you're going to go deeper and hotter, and you're going to produce, that megawatt number is going to go from 4 to 8 to 16 to 20 to 30, and then we're going to start to think about having multiple wells in one location. So in Taiwan we see that you have a lot of population, But where you don't have population, you also have very mountainous terrain that's tough to get to. So we're going to probably have to think about directional drilling, where you have a pad with lots of wells on it, and the well goes off. Rather than having lots of rigs dotted around the mountains and cutting down the forest, we're going to have a location with lots of wells on it, and we're going to make the well go directionally off. And so we will talk about some of that. So that's our conventional. Taiwan will probably move to EGS and AGS further down the road, yeah, in the learning curve. And what you heard people talk about yesterday was GA, geothermal anywhere, yeah. And that's the idea being is that once you've exploited your conventional resources and you understand how that system works, and you want to generate more energy from the places where the rock isn't so fractured, then you start to drill deeper into the ground, and maybe you drill a pair of wells and you do EGS, which is where we fracture between the rock. So we're going to drill a deeper well with a bigger rig, go deeper and fracture between the rock, and we're going to create a man-made heat exchanger. So then we pump cold water down one side, it passes through the fractures in the rock, lifts up that heat, there's a huge amount of heat under this country, and then turns that back to steam. You want to say something, Kim?
Just a very quick comment, Tony. From the IABC, which is the International Association of Drilling Contractors, the nomenclature that they're currently favouring for their standards is going to be reservoir dependent and reservoir independent geothermal. So they're looking at that.
So we'll change conventional. So it's no longer conventional. So it'd be reservoir dependent, and then unconventional will be reservoir independent.
Because the problem with the unconventional label is that actually very quickly that's going to be conventional, and you need a standard that's robust over time. So it's a very small nomenclature point, but just something.
Yeah.
Since they're really fractured and Taiwan geology is really fractured, so sometimes we don't know. It's either it's like hard rock without fracture, or like with okay reservoir or really good reservoir. Does it make any sense that we do like a hybrid? That does it make any sense, or
yeah, absolutely. Everything that we do, even in what we think is hard, massive bodies of rock, there are a surprising number of fractures, and that's one of the things that we're finding with particularly large granite bodies. Large granite bodies are much more fractured than we traditionally thought they were going to be, and as we do more geothermal in hot dry rock, as it used to be called, we're finding that actually there's a lot more fractures than we initially thought. And do you want to have a...
Well, I was going to say some of the earlier projects of EGS, and maybe Anne knows more about this, were actually in some of these systems where maybe you had some fractures, but you didn't have the permeability that you needed from a hydrothermal system point of view, and then they were trying to fracture and enhance that permeability. And some of the latest projects that we're seeing in US, they're looking at potentially applying artificial stimulation, hydraulic fracturing in existing hydrothermal systems. So what you're saying is it's completely...
So generally speaking, it's a plus for the fracture system we have here. Even for GS, right?
Yeah.
Yes.
Yeah.
It doesn't have to be.
And then the last one is a directional driller's dream, because we get to be kept really busy. Is what was called AGS, Advanced Geothermal System, which is the other nomenclature for it is closed loop. So what we do there, I'll grab that for us.
Yeah.
Is we drill one borehole down here, then we drill the second borehole down here, and we connect them together. We either connect them together like this, or we connect them together like this. Now, the way we do that is typically this well has either casing in it that's made of metal, or it's open hole but we have magnets in it. This well has a magnetic ranging tool. that knows where this well is. So we get down here, we see this well is here, and then we take measurements here, and it tells us how far and what angle that well is from us, and then we steer that together, and we make those wells connect. So a project doing that is ongoing in Germany today. And actually the Schlumberger folks here are the ones doing the magnetic ranging.
Yeah.
Cool. So here's some of those differences between EGS and closed loop. But the way I look at it, really, I believe that we're going to have a situation where we have hydrothermal opportunities that are still absolutely applicable in the world. Then we will have EGS between a certain temperature range where the rock is easily to be fractured, rock type or temperature range, and we create a fracture network that produces the most amount of power. And then when we get very deep in certain places in the world where we don't have enough energy in that shallow, we go down into very hot rock that is at the brittle ductile boundary, which is probably going to be a long time in Taiwan's future. I think you've got plenty of shallow, high heat level resources here, very lucky. And then we'll do closed loop very deep, because the rock won't be fracturable in a long-term sense. So I think that is the journey we were going to get, but that's my theory. But there are challenges and benefits, and if you're in a very mature room full of a lot of geothermal people, you can have a little bit of a scrap about this, yeah? So there's a lot of opinions and a lot of things out there, but all geothermal is good, okay? Yeah. So we have no problem with that. And we are all of us in this room are in the hole making business, yeah? That's what we're going to do. We're going to make a hole, and we're going to fracture the rock or not fracture the rock, and we're going to get as much heat out as we can. So some of our challenges, yeah? This is what everybody in this room who's going to move into developing the resources in this country. Rig capabilities. In US land today, there are 700 rigs drilling, yeah? And the gentleman, the drilling engineer in the back, said that we're a little bit less than 10 in the country. So we are going to have to get a supply chain going into Taiwan. And Taiwan, obviously, you have massive manufacturing capability, yeah? So get with those drilling rig companies and build some of your own rigs, yeah? You've got the infrastructure. Get a partnership going with a rig manufacturer and put a facility in place and build your own rigs that are suitable for Taiwan.
If anybody's interested in that process, Tony and I are in discussion with various rig manufacturers. We're more than happy to make those connections for the country, to bring those people, those experts into the country. They're going to be really happy to have a manufacturing agreement in the country here, because it's perfectly located. One quick question, one quick comment on rig capabilities. One of the other jobs I do is subject matter expert for legal cases concerning drilling. I've sat in a court in Holland due to a rig capability misunderstanding. A bottom hole assembly fell apart, and the client blamed the vendor company for that failure. What had happened was the client had specified a really good drill bit, a really good motor, forgotten that the rig couldn't drive it. So we couldn't put the weight on bit that was required. And because we couldn't put the weight on bit that was required, because of the lack of capability of the rig, we had severe shock and vibration, and the bottom hole equipment fell apart. But the root cause, one of the root causes of that, was the rig was not capable of driving the new technologies to the level they needed to be driven. So we've got to be careful when we select our rig that it is genuinely fit for purpose for the new technology we're going to select.
The next thing we have to think about is temperature management. Now, heat is good because that's what we want, yeah? But to get there, we have to really think about how we're going to drill this well in the right place, at the right speed, with the right technology. So there's two ways to attack temperature. One is having the specifications of the equipment in the hole to have very high temperature ratings. But that is only going to get us to about 200 degrees centigrade. So after 200 degrees centigrade, we have to do something to keep the well cool. And I've got coming up in the slides how we can manage that temperature. High temperature electronic tools, they are now building those. So there's a large fleet that have 175 degree capability. There's a few that have 200 degrees capability, and there's a few in design that are going to 210 to 225.
But Tony, they're really expensive, aren't they? Those high temperature tools, they're going to be very expensive, surely.
But I think, Kevin, if we have to spend 5 million on an insulated drill pipe string, and we have a 175 degree tool in the hole, we can save on the insulated drill pipe.
Yeah, but you've got the patent for the insulated drill pipe. It might be better that we buy the insulated drill pipe. So it's a balance, just a silly interaction there, but it's a balance of what makes best economic sense for your location and your well and your temperature profile. We've got high temperature tools, that's an answer. We've got insulated drill pipe, that's an answer. But the selection of the technology and the balance of the technology is going to be unique to your project.
And it jumps back to rig capability as well. Because one of the most cooling things that we have is just taking that nice cold fluid that we have on the surface and getting it quickly to the bottom. So if we have too smaller pumps on the rig, we have too lower pressure system on the rig, we can't pump quickly. The fluid warms up on the journey down the hole and we fry the tools. So unfortunately, or fortunately, all these things are interrelated. Yeah.
And just one very quick point. If your tool is temperature rated to 150 degrees, I'm just making a number up here, and you take that tool to 150.05 degrees,
you buy it.
You just bought that tool.
Yeah.
And that tool might be $1.5 million. Inside that tool there will be little thermally active stickers, and if any of those have activated, you bought the entire tool, because the vendor company that's renting you that equipment can no longer be certain that that tool is fit for purpose for the next operation.
10 minutes? I don't think we have 10 minutes. I think we have...
we're supposed to be till 11.
No, we're till 11. Ignore the 10 minutes, yeah. No stress, yeah. Casing, yeah. So we're going to run, we're going to drill a section. So we drill a 17.5-inch section. We put 13 3/8 casing in. These are just normal oil and gas. We drill a 12 1/4, we put 9 5/8 casing. So these casings, these steel casings that we put in the ground, they have specifications for certain temperatures. Yeah? So as we go hotter and hotter, that casing has to be derated. Yeah? So we have to pay a lot of attention to what are the temperature impacts on the steel that we're putting in the hole. The other thing we have to think about casing is how long is our well going to last? You know, as a geothermal operator, we want our well to last for tens of years, 25, 30, 35 years. We have to think about corrosion, okay? We have to think about the chemistry of the fluid coming out of our well, and how is that chemistry attacking our steel, or something more exotic than steel. So around the world, we see on geothermal projects, we have very exotic materials. In California, the fluids coming out of the well are unbelievably acidic and caustic and nasty. Yeah, they have to spend a lot of money on casing, but that money is well spent because the well lasts longer. So again,
the wells produce a lot.
And the wells produce a lot. So again, it's all about cost effectiveness and value.
Tony, can I just throw a
no, you
quick
can't. No, you can't.
Please,
Shush up.
please. Okay.
So the next one is high temperature cement. So I've recently been studying high temperature cement, and basically there is a higher degree of confidence now coming into it. So again, simple things. Portland cement, actually from 110 centigrade onwards, it's used to 200 degrees centigrade, but from 110 onwards, it starts to lose its bond capability, yeah? So as we move up from 100 to 200 to 300 to cement in our casing, we have to think about the chemistry of the cement. So we have to think about using silica flour. We have to start thinking about the products and the materials that come from the coal production and steel production. Those minerals made into cement actually bond better at high temperature than regular cement. Cement is so important for geothermal wells because we have this steel tube in the hole, and that steel tube has got high temperature all running up and down it, different temperature gradients. Steel expands, yeah? So it's really, really critical that we cement the casing in place properly, yeah? And that cement job in geothermal wells is typically all the way back to the surface. In oil and gas, we typically put a casing in the hole, and then we just lift the cement up maybe 500 feet, 150 meters to secure the bottom of it, and we have an annulus. That gap in geothermal with the temperature means that that fluid in that gap, or if fluid gets in there, it expands, and then what happens to our casing? It collapses, yeah? So there's lots of jobs around the world that have the casing was derated because of the temperature, so it's become softer because of the heat. It's got fluid on the backside, that fluid heats up and the casing collapses. So if we go all the way back to where Kevin started in this process, those things must be understood. What is the life of our well? What is the temperature of our well? How long is this tubular going to last or need to last in this hole, so that we make our economic model based on the life of our geothermal project? So we have to spend potentially more to increase our value. Yeah, so it's a tricky thing. You want to add something?
Yep. Yeah, I was just going to say we've got two different client approaches to casing selection. The first client, I won't name them, said we can't afford the expensive corrosion-resistant alloys required, so we've not put those into the project costing because we're not going to get the investor. So they went with standard L80 casing. I think it was about 12 months later they were in the well trying to repair it. Another client is specifying titanium. Titanium is so expensive, the costings are astronomical. But there are other solutions. Don't just look at the metallurgy. We've got glass fiber linings that we can epoxy cement into place. We can use standard cheap steel casing and protect it against the fluids. So don't just be forced down an expensive corrosion-resistant alloy route or a simple steel route. We've got different combinations of corrosion protection.
Coatings on the inside of the pipe.
It's not strictly a coating. It's a separate glass fiber tube that is epoxy bonded inside the casing.
It's for district heating, maximum temperature of 110 degrees C.
Yeah. But the beauty of that product, other than a straight coatings are easily damaged by interventions into the well. So the glass fiber lined option is very robust against well intervention.
So just to give you an example of rig sizing, this should be a proper exercise, but if we were going to drill a 8,000 meter well in Taiwan, we would need a rig like the Doyon 26, which is drilling in Alaska long ERD wells. Now, all the orange stuff is winterization, but that rig is absolutely huge, and the specifications on it as a land rig, that rig is still going to cost you in the order of $100 million, yeah? Okay, just to give a scale. But in the rig sizing and the rig technology exercise, one of the things that I have been frustrated with in my geothermal career is people not spending $1,000 or $500 on data acquisition. Okay, so you can have a cheap rig, or a good enough cheap rig, but you put some good data acquisition on it, and you put a good auto driller on it, and you improve the capability of that rig massively. Yeah, so think about where if you have a limited budget, think about where you spend that money, and some automation and some data acquisition and some electronics on it can come relatively cheap and give you a big jump in performance. Yeah. Some plugins you're going to have to think about. If you've got the rig there, you're going to have to potentially have mud coolers. Yeah, you're going to have to put a cooling system on the surface because the fluid is coming back. So you have to understand, how do those coolers and things plug into that rig. You may have to do a process called managed pressure drilling. So if you've got lots and lots of losses, you can potentially drill the well underbalanced and reduce those losses, but you have to have a plug-in of a managed pressure drilling system. Yeah. Particle impact drilling. That's where you inject steel shot into the fluid system. It comes down, comes out of the drill bit and breaks the formation, and the steel balls come back to the surface and they're filtered out. That is a plug-in. You need a particle impact drilling. You're going to have to think about the location to take all this. And if your equipment is coming out of the hole and is so hot that it will hurt the hands on the rig floor, maybe we have to think about some level of robotics. Yeah? So there are some robotics packages now that are designed for land rigs that are not that expensive. Yeah. Yeah.
Can I add a couple?
Yeah, sure.
One thing maybe I would add is, especially in hydrothermal systems, is the fact that you might get into a well control situation. So components that can withstand better the temperature, especially the BOP, is very important. Because typically, if you go with a standard rig from oil and gas, that's not going to do it. And maybe also the procedures, how you manage a well control situation as well, are very different.
Yeah. Can I just make a very quick comment on that? If anybody's using standard oil and gas well control equipment, the standard is an API standard 6.8. The maximum temperature that equipment is fit for purpose to is 121 degrees centigrade. The other thing is, going back to our procedures, and you mentioned it, and thank you for the question, we should never ever do what we call a hard shut-in with a blowout preventer. Blowout preventers are not designed to close against a flowing well. We should always do what we call a soft shut-in with an open choke. If we do a hard shut-in on a geothermal well, we will destroy the seal face of the BOP as we try and close the BOP ram. You must close the BOP with an alternative flow path open through the choke and then close the choke. Never, and in oil and gas we shouldn't do it anyway, but we do have a discussion in oil and gas between hard and soft shut-in, but BOP and well control is critical as well.
The most common piece of safety equipment in geothermal is diversion. Yeah. So we've lost our fluid in the hole into the formation. We got lots of heat. We're turning the water in the well into steam. The most important thing is that steam doesn't come out onto the rig floor. That steam comes out off the rig site with our diverter. Yeah. So it's a very simple thing, but it just gets the steam away from the people safe. Right. Our next geothermal challenge, and we sort of talked about this, is radar penetration. So just to give you a complete update, conventional drill bits are the most common way of drilling, but just to give you some of the future technologies that we've got. So this is as we talked about drill bits when we were talking about the process, these are the different types. So here's our roller cone bit. Here's our PDC bit, and these are these absolutely fantastic three-dimensional type cutters that we have now that look a lot more like teeth, that can get into that metamorphic rock, those meta-sediments, into the basement rocks that you have in Taiwan, and really break through that rock quickly. But if we're starting to drill bigger and more exotic hole types, then we have to go to a bit that has potentially multiple different diameters on it. So the narrower part of the bit fails the rock effectively. It then de-stresses the rock behind it, and the second set of cutters can then break the de-stressed rock. So if we'd had a bit that was full size on its own, it would have drilled slower than the two-stage type of bit. And then this was a bit called particle impact drilling. So you fire these balls out of the end, the balls break the rock, and then the PDC cuts the rock behind it. So this is called particle impact drilling. And this is the system. So you have like a cement mixer, injects the balls in here, they go up, down the rig, down the hole, down the drill pipe, blast the rock, and the little balls come all the way back up, come over the shakers, and then go round. So it's a completely closed loop system. The other types out there. So there are new technologies being worked on. So you have plasma, okay? So there's a company called GA Drilling that drill with plasma. The most likely way that plasma will go over the next few years is a combination of PDC plus plasma. So the plasma will weaken the rock, and then the PDC will drill it. There is a millimeter wave, which is a company called Quaise out of MIT. Millimeter wave is like a microwave energy going down the pipe and breaks the rock. And these are all in R&D stages. So, you know, it's the latest technology that's out there, and I think you all get copies of this anyway, so you can look into that. But advanced conventional is literally the cutting edge, no pun intended. Advanced conventional is most probably the products you're going to use, yeah? But those advanced conventionals have really gone in the last year or two from 10 meters per hour to 30 meters per hour. So that means your well is going to take you 1/3 of the time that it was just a couple of years ago. Yeah, so it's a good point.
Yeah, the benchmark now is 40 meters an hour in high compressive strength granite. So, and that in the next 2 years, that will be 80 meters an hour, no problem.
So then for our drill string, we have lots of different ways of getting this cooling to the bottom of the hole. And I kind of got into this because I was working with the National Renewable Energy Lab in Colorado on making very high temperature electronics, 400 degrees C. We just looked at the ability to make those electronics, and this is a country that makes chips, yeah? You know, you are the chip making dudes and dudettes of the world, yeah? I could make a chip that would survive at 400 degrees C, but there's no way in Taiwan that they were going to make those chips for me, because I only would want 1,000 of them, yeah? Taiwan makes chips for people that want 5 billion chips, yeah? So we had to think about it differently. So we had to think about, how do we get cold fluid to the bottom of the hole? So the first thing we looked at was coatings, yeah? So now you can put a coating on the inside of the pipe that has a much lower heat coefficient than steel, super low, yeah? And I'll show you how that progressed. There are 2 manufacturers of insulated pipe out there. So having a pipe with a pipe inside it, with an insulative layer between it, means that we can get colder fluid to the bottom. We can combine that with mud coolers on the surface. So mud coolers on their own, with just normal pipe, the mud will warm up on its journey to the bottom of the hole. But if you now combine mud coolers with coatings, if your well is maybe 225 degrees C, maybe you only need mud coolers and coatings, yeah? And the rig pumps. As you go hotter and hotter, you would then go mud coolers, insulated pipe, and coatings, yeah? So you combine technologies together. And maybe you go mud coolers, big diameter insulated pipe, big diameter pipe with coatings. So you get the fluid faster to the bottom of the hole. So there are lots of people around the world working on these sort of technologies to give the folks in Taiwan a head start, okay? believe it or not, one of the most insulative processes if you have laminar flow in the outside of the hole. So when we're pumping liquids, we either have turbulent flow or we have laminar flow. When we have laminar flow, the flow of the fluid coming up the wall insulates the pipe. When we have turbulence, that heat transfer from the rock goes into the pipe, into the fluid going down there. So if we design our well engineering program that the annulus has laminar flow in it, has a big impact on keeping the well cool. The other conventional geothermal insulation is lost circulation. So when you lose circulation in the wellbore and the fluid level drops, you have a gas or an air gap between the rock and the pipe. So the actual fluid in the pipe doesn't get so hot because of the gas on the outside. So in summation, temperature management now is becoming much more cost effective, and we have the ability to get to very high temperatures. So a team working for me last year modeled this when we were working on insulated drill pipe, and in a 400 degrees C well, we modeled that the fluid would come out of the bit at 135 degrees centigrade. So we could keep the whole system cold. But what happens when you drop an ice cube into a coffee cup? It goes. When you hit super hot rock with cold fluid, the rock goes as well. So a tiny thin layer on the top of the rock gets a thermal impact. And there's some really good work done by the University of Tokyo and University of Texas on that thermal impact. Yeah. So now if we had, as Kevin was saying, 40 meters per hour with a PDC bit, we may have thermal impact on the rock that improves that cutting ability of that rock. So we get cold fluid to the bottom of the well, we keep all the tools cool, keep them safe, and then we thermally impact the rock with cold fluid. So, you know, we can even improve our, you know, normally in drilling, the ROP goes down the deeper and deeper you get. We may have the inverse of that sometime in the future where the ROP starts to go up with depth. Yeah,
yeah, just a quick one as well. In terms of the survivability of your cutters, the cooler you keep them, the longer they're going to last. And one final comment on the slide is when you're doing your rig selection, part of the rig selection is the drill string, the drill pipe that you're going to use on that rig. And you cannot believe how important the drill pipe selection is in terms of its size, its grade, its connections, but also its coatings. So absolutely crucial to drilling performance is drill pipe selection from a huge range of things, but we haven't got time to go into that.
And its age.
And its age, yes,
and its age,
absolutely.
Yeah. So this was the big jump that went with coatings. So coatings originally, go back, can I go back? Yep. We had a thermal coating with a 0.83 watts per meter Kelvin, and that is now down to 0.18. Yeah. So a huge jump in the insulative capability, and this is something that has to be put on pipe anyway. So all you say is rather than the regular coating, I'll have the low heat coefficient coating, and it's not really very much expensive. So it's a very, very cost-effective way of cooling your borehole. Yeah. Insulated pipe. So this is what it looks like. It has a pipe inside a pipe with a rubber around the outside, and that can keep you completely insulated to the bottom of the wellbore. Here to give you just a little bit, you can see what the differences are in different materials, yeah. And the shocking one to me when I first looked into this was the difference between pipe steel and a Inconel piece of steel. So alloys can have a much lower heat coefficient, so you don't have to make the whole pipe out of Inconel. But if the tool joints, which are the very thickest part of the pipe, you coat them with Inconel, it can have a big impact on it. And the impact is this, okay? So to reduce the heat loss, you strive to improve the porous selection. So on this gentleman in Norway, he's not going to be any warmer if he puts another jacket on, yeah? So he needs a pair of trousers to be able to insulate it. So what we see when we model the whole drill string is the tool joints. We have to do something in the tool joints. If not, it's like having a window with a hole in it and the heat comes in or the heat goes out of that hole. We have to have protection on the tool joint, which is the most important spot. Completions is a really interesting problem, yeah? So completions equipment has lots of seals in it, and seals and rubber has really has low temperature limitations. So we have to think about in a geothermal well, think about our completion, yeah? Do we need any completion at all? Do we just have a slotted liner? Do we have a bare hole? Can we cool the well down while we're drilling? And as we get hotter and hotter and we're using colder and colder fluid, can we cool it down, run the completion in the well, do our EGS, do our fracturing, then as the well heats up, we destroy the completion, but we did the magic first already, yeah? So there are people out there in the world looking at how can they re-engineer the completion to have metal locks on the completion so that we can do our magic, the completion locks itself, we can never re-enter it like we would in an oil and gas well, but we have done the magic that we need to improve the permeability, fracture our rock and improve our thing. So completion is becoming less of a challenge as well. So you want to add quickly to that, or no? Okay. We're on 5 minutes, yeah. So cement and casing, and really what I want to leave you with is in Taiwan, you're going to go through a learning process of getting hotter and deeper. And while you're doing that, keep up to date with the technology coming out around the world, because the whole geothermal ecosystem that is out there at the moment, everyone else in the United States and UK and Kenya and New Zealand are having the same challenges as you, and there's a whole global workforce working on solving these problems. And you know, we were really excited, Kevin and I, when Karen invited us to come here to Taiwan to give you just some insight that the world is there helping you as well, and go and steal their ideas. Yeah, absolutely. Oh, we want to give you those ideas. It is actually, you know, it is so important that our industry, that we're all in here, we help each other, because we are where oil and gas was 100 years ago, yeah? They've been learning for 100 years, and geothermal has a long history, but it's going to steal efficiencies from shale drilling. Shale was an uneconomic resource that unless we drilled fast, we couldn't make any money doing it, yeah? Geothermal's economics are sometimes challenging, but the faster we drill, the lower the cost we have. So to the geothermal operators in the room, you know, you do not have to accept mediocrity in your drilling program. You want to drive them for performance. So sometimes think about how are you going to reward them in that. So a contract that rewards them for drilling fast could be something that you think about. Yeah,
I would say actually that in 5 years' time, it's a bold statement, but in 5 years' time, geothermal will be blowing away oil and gas drilling performance. I absolutely see that, because the requirement for longer and longer well bores, faster and faster in hard, challenging environments. I think we are genuinely going to be showing the oil and gas industry the backs of our heels very soon.
Cool, that's it. Thank you very much.